Imagine you have this incredibly complex, mathematically perfect secret code.
Right, like something that secures the most sensitive information on the planet.
Yeah, exactly. But, there is this fundamental catch built into the physics of it. Every single time you want to verify that the code actually works, the process is so computationally heavy and, well, physically destructive to the data that it would take you a million years to read it.
Which means you're left with this ultimate theoretical tool, but it's trapped behind an entirely impractical physical barrier. I mean, the security means nothing if you can't actually verify the state of the system holding it.
Right, but what if a research team figured out how to just, bypass that million-year process? What if they handed you a physical optical filter that let you verify the entirety of that quantum code in a single instantaneous measurement?
And without destroying the underlying pattern, yeah.
Yeah.
That completely shifts the conversation from abstract quantum theory to, well, viable, scalable quantum engineering.
It's massive. So welcome back, Deep Divers. Today we are unpacking a major, long-standing bottleneck in the world of quantum physics that scientists have finally managed to crack.
Yeah, it's a really exciting one. We're looking at a breakthrough published in Science Advances by researchers from Kyoto University and Hiroshima University.
And it is potentially paving the way for real-world quantum teleportation and, unhackable global network.
Exactly. We're going to explore the mechanics of a specific quantum state, the historical nightmare of trying to measure it, and the elegant optical shortcut these researchers designed to read the state in a single shot.
So by the end of this class, you will understand the physical difference between standard entanglement and the highly resilient W state, and also how a concept called cyclic shift symmetry allowed scientists to basically rewrite the rules of quantum measurement.
It's a lot, but it's fascinating.
It is. So grab a notebook or just get comfortable and think along with us. Oh, but before we hit the whiteboard, please help the classroom grow. You know the drill, subscribe, click on our affiliate marketing links, grab some of our exclusive fourth wall merchandise, and definitely suggest new topics for us to cover in the comments.
We love seeing those suggestions.
We really do. All right, so let's get into the physics. We need to start with the target of this Kyoto and Hiroshima experiment, which is the W state.
Right. So assuming you're already familiar with the basics of standard quantum entanglement, the concept where measuring the state of one particle instantly dictates the state of its entangled partner.
Which is spooky action at a distance, right?
Exactly. Well, we need to look at what happens when you scale that up. When you entangle 3 or more particles, you enter the realm of multipartite entanglement. And traditionally, the most famous version of this is the GHZ state.
The Greenberger-Horn-Zeilinger state, yeah.
Yeah.
But the GHZ state is famously an all-or-nothing proposition, isn't it?
It really is.
Because in a GHZ state, the quantum superposition is highly centralized. So if you lose a single photon to environmental noise, or if just one particle interacts with the outside world, the entire entangled system just decoheres.
Poof. The wave function collapses, and your whole quantum link is gone.
That sounds incredibly fragile.
Oh, it is. And that extreme fragility is the primary hurdle in scaling up quantum technologies right now. I mean, you can't build a global quantum internet if the loss of a single photon in some fiber optic cable across the Atlantic brings down the entire network.
Right, that would be terrible. So this is where the W state comes in.
Yes, because the W state fundamentally changes the architecture of the entanglement.
Because it distributes the superposition differently across the particles, right?
Exactly. So in a W state involving, let's say, 3 photons, the system is in a superposition where only one of the photons is excited, but you don't know which one.
Okay, so the excitation is equally shared across all 3.
Right. And the consequence of that distribution is just this profound resilience. If you have a group of particles entangled in a W state, and one of those particles is lost or destroyed...
Well, the remaining particles don't entirely decohere.
Exactly. They actually retain a degree of bipartite entanglement.
Oh, wow. Okay, so if standard multipartite entanglement, like the GHZ state, is like a delicate glass chain where one shattered link completely severs the connection,
Sure.
then a W state is operating more like a team of mountaineers scaling a cliff.
Oh, I like that.
Right. Like they are all roped together in a distributed safety system. If one climber loses their grip or, even if their specific carabiner snaps, the rest of the team doesn't automatically plummet.
No, because they're still anchored.
Exactly. The remaining climbers are still safely tied to the mountain and to each other. The structural integrity of the group actually survives the localized failure.
That captures the mechanics really well, yeah.
Yeah.
The overall entanglement survives the loss of a subsystem.
Yeah.
And when you apply that to quantum communication, well, the W state becomes the holy grail.
Because you're always going to lose data.
Exactly.
Yeah.
In any physical communication medium, whether you are firing lasers through the atmosphere or, transmitting through physical fiber, photon absorption and scattering, are physical inevitabilities.
So the resilience of the W state acts as this built-in fail-safe for node failures in a quantum network. Like if Tokyo drops a packet sent from New York, the quantum state shared by the rest of the global nodes remains totally intact.
Which is an incredible feature for secure distributed computing.
Okay, but if this W state is the ultimate safety rope for a quantum internet, the fact that we aren't using it globally right now tells me there must be a massive catch.
Maybe you're right.
Let me guess. The math scales poorly when we actually try to read or verify the state.
Oh, it is brutal. The measurement process has been an absolute bottleneck. For decades, the theoretical advantages of the W state were basically overshadowed by the sheer misery of trying to measure it.
Misery is a strong word for physics.
But accurate here. To verify a complex quantum state, physicists historically rely on a technique called quantum tomography.
And tomography is essentially statistical reconstruction, right? Because of the wave function collapse. Like you can't just look at a multi-photon quantum state and read all of its properties at once.
Right, because the act of measuring it forces the superposition to pick a definite state.
Which destroys the very entanglement you're trying to observe in the first place.
That is the core of the problem. So to understand the original uncollapsed W state, you have to build a statistical density matrix. You prepare the exact same W state, measure a specific property of photon A, and note the result.
And then the state collapses?
Yep. Then you have to generate a brand new identical W state. This time you measure photon B. The state collapses again.
Oh, wow.
And you just repeat this process an exponential number of times, measuring different observables from different angles, so to speak, to slowly reconstruct the mathematical picture of the original state.
Okay, let's visualize that process for the deep divers. It is like trying to map the precise architectural layout of a massive pitch-black warehouse. And you're only allowed to carry a tiny, incredibly dim laser pointer.
Good analogy.
You walk inside, click the laser on for a split second, and you illuminate like a single square inch of a cardboard box. Then you are immediately kicked out of the warehouse.
Right.
So to map the entire facility, you have to go back in, stand in a slightly different spot, and flash the laser pointer again. You'd have to do this millions of times just to generate enough data points to deduce the floor plan.
And taking that further, consider the scaling math of that tomography. The number of measurements required grows exponentially with every single particle you add to the state.
Ouch.
Yeah. If you are dealing with 2 or 3 photons, tomography is annoying, but it's, manageable in a lab setting over a few hours.
But if we're talking about building a functional quantum computer, we need hundreds, if not thousands, of entangled qubits.
Exactly. And at that scale, the tomography workload doesn't just become difficult, it becomes physically impossible. If adding just one more photon doubles or triples the required number of measurements, a 100-photon system would require more time to verify than the current age of the universe.
Wait, really? More than the age of the universe?
Yes. The traditional measurement protocol fundamentally breaks down. It traps the W state as just a theoretical curiosity.
So we have our unbreakable code, but verifying it takes 1,000,000 years.
Okay.
Which brings us back to the Science Advances paper. If measuring the individual particles takes too long because of wave function collapse, you'd have to, stop looking at the individual trees and start looking at the forest.
Right.
Did the researchers from Kyoto and Hiroshima find a macro property of the whole state to measure instead?
They did. They realized that brute forcing the individual particles was just the wrong approach. They turned their attention to a shortcut called an entangled measurement.
Okay, what is that?
In theory, an entangled measurement allows you to bypass tomography by performing a single global operation on the entire system at once.
Ah, so if tomography is the dim laser pointer in the dark warehouse, an entangled measurement is walking in and just flipping on a stadium floodlight. You capture the entire state in a single glance.
Exactly. The problem is that while physicists knew entangled measurements were mathematically possible, and they'd even built optical floodlights for the GAZ state, no one had been able to engineer one for the W state.
Really?
Yeah, it remained an unsolved puzzle for 25 years. The breakthrough happened because Shigeki Takuchi and his team decided to focus specifically on a hidden pattern within the W state called cyclic shift symmetry.
Cyclic shift symmetry. Okay, let's break down the mechanics of that.
Okay, let's look at a three-photon W state. The photons occupy specific positional modes, which we can label simply as position 1, position 2, and position 3.
Got it.
Because of how the superposition is distributed in a W state, the mathematical description of the entire system possesses this unique rotational symmetry.
Meaning what, exactly?
Well, if you physically shift the positions of the photons, like moving the photon in position 1 to position 2, moving 2 to 3, and cycling the photon in position 3 back to position 1, the overarching quantum state of the system remains entirely unchanged.
Oh, I see. It's like playing a musical chord on a piano. Like if you play a C major chord in its root position, you strike C, E, and G.
Right.
But if you take that bottom C and move it to the top of the voicing, so you're playing E, G, and C, you've changed the specific positions of the notes. But the harmonic relationship, the macro property of the sound, is mathematically still the exact same C major chord.
That's a highly accurate way to conceptualize it, actually. The harmony remains symmetric, despite the positional rotation.
So the Kyoto team realized they didn't need to measure the individual notes of the W state?
Exactly. If they could build a device that solely detected the presence of that specific cyclic shift symmetry, the specific harmony, they would instantly know they had a W state.
And without having to measure the individual photons and trigger a massive wave function collapse? Yeah.
Exactly.
But wait, how do you actually measure a mathematical concept like symmetry in a physical lab? You can't just run a line of code on a physical photon. You have to build actual hardware.
And this is where the theoretical physics translates into just brilliant optical engineering. The researchers designed an intricate optical maze that performs a physical Fourier transform.
Okay, let's unpack the optical Fourier transform. In mathematics, a Fourier transform basically takes a complex signal and breaks it apart into its constituent frequencies. How does that work with physical light?
Well, they constructed a highly specific network of optical components, primarily utilizing precisely aligned beam splitters and phase shifters.
Okay.
When a photon hits a beam splitter, it doesn't just bounce off or pass through. In the quantum realm, the photon enters a superposition of taking both paths simultaneously.
Oh man, so it's forced to explore the entire maze at once.
Yes. And as the photons travel along these different paths, they encounter phase shifters. A phase shifter physically delays the photon's wave function by a microscopic fraction, altering the timing of the wave's peaks and troughs.
So you have these multiple photons existing in a W state, split into superpositions, navigating this physical network, and having their wave phases mathematically altered as they go.
Right. And here's where the symmetry creates the shortcut. When these modified split wave functions inevitably recombine at the various intersections of the maze, they undergo quantum interference.
Constructive and destructive interference.
Exactly.
Like dropping two stones into a pond. If the ripples meet peak to peak, they amplify each other. But if a peak meets a trough, they cancel each other out, essentially creating a flat surface.
Spot on. So the Kyoto team engineered the beam splitters and phase shifters so that the resulting interference pattern is perfectly tuned to cyclic shift symmetry, meaning if the three incoming photons actually possess the cyclic shift symmetry of a W state, their recombining wave functions will destructively interfere at almost all of the possible exit routes of the maze.
Oh, wow.
Yeah, the waves cancel each other out entirely at those exits, meaning it is physically impossible for a photon to be detected there.
So the maze restricts their physical options based on their mathematical properties.
Exactly. Through constructive interference, the wave functions amplify each other at one specific output port. The physical hardware physically routes the photons based on their symmetry.
That is wild. The photons basically declare their state by which door they are forced to exit.
Yep.
You don't have to measure the particles and rebuild a statistical matrix. You just check which detector clicked at the end of the optical maze. If detector A clicks, the physical interference guarantees that the input was a highly symmetric W state.
And that single click is the entangled measurement. It is the floodlight. They bypass the need for exponential data collection by making the quantum interference do all the computational heavy lifting.
And the team actually built and validated this hardware, right? They didn't just model it on a supercomputer.
No, they actually did it. They implemented a stable physical three-photon setup in the laboratory. They generated the photons, entangled them, routed them through the optical Fourier transform, and consistently achieved a single-shot detection of the W state.
That's incredible.
It is. The stability of the system is a massive achievement in quantum optics, proving that this optical network can operate reliably without constant, microscopic recalibration.
Which represents a monumental shift in how we approach quantum architecture.
Yeah.
We took the resilient mountaineer rope of the W state, and we finally built the specific pair of glasses required to look at it without causing it to vanish.
Beautifully put. So we can sort of synthesize the key takeaways from this breakthrough to understand why this matters for the near future of tech.
Let's do it.
The first major takeaway is the distinct advantage of the W state over standard multipartite entanglement. Its distributed superposition allows it to survive partial particle loss, making it the ideal candidate for real-world quantum communication where signal degradation is just unavoidable.
Right. And the second takeaway is the sheer inefficiency of traditional quantum tomography. Reconstructing a wave function after its collapse requires exponential scaling, creating a literal impossible bottleneck for anything larger than a few photons.
And the final takeaway is the power of the optical Fourier transform itself. By focusing on the hidden pattern of cyclic shift symmetry and using beam splitters and phase shifters to force constructive and destructive interference, the researchers achieved a single-shot entangled measurement.
They basically replaced millions of measurements with one physical routing operation. The implications of solving a 25-year-old measurement problem are massive. I mean, this isn't just an academic victory, is it?
Not at all. This single-shot measurement is a prerequisite for highly advanced protocols like quantum teleportation.
Right, because in quantum teleportation, you're transferring the exact quantum state of a particle across a distance without moving the physical particle itself.
Exactly. And that requires incredibly precise, instantaneous measurements of entangled pairs. If you are stuck doing tomography, real-time teleportation of dense data is literally impossible. This new optical network clears that roadblock entirely.
It also opens the door to truly secure distributed quantum computing. Like, we can envision a future where smaller quantum processors linked across different cities can share the computational load of a massive algorithm.
Yes, and to do that securely, they need to share multipartite entanglement.
Yeah.
And they need to verify that entanglement instantly before running the calculation.
And the laboratory demonstration by Takeuchi's team is basically the proof of concept for that global infrastructure.
It is. And the next engineering phase is already underway, which brings us to, I think, an interesting exercise in lateral thinking for the listeners.
Yeah, let's hear it.
The researchers solved this seemingly impossible measurement bottleneck, not by attacking the individual photons with more computational power, but by stepping back and looking for the overarching symmetry. They let the natural physics of interference do the work for them.
So think about the problems you are currently facing, whether in a complex engineering project, your daily workflow, or even just your personal routines. Where are you trying to brute force a solution?
Right.
Where are you exhausting resources by trying to manage every single microscopic variable when stepping back to look for a broader pattern, a hidden symmetry, might reveal a shortcut that solves the problem in a single step?
It's a really powerful reminder that sometimes the barrier isn't a lack of effort, it's a rigid perspective. The math didn't change, but the angle of approach did.
Exactly. Practice that kind of lateral thinking this week. We would absolutely love to hear your reflections and your answers to that thought experiment down in the comments.
Me too.
And in our next deep dive, we are going to explore the immediate future of this specific hardware. We're going to look at the engineering challenges of taking this massive table-sized optical network of beam splitters and phase shifters and shrinking it all down into microscopic, compact photonic chips.
Which is huge. Taking the breakthrough out of the sterile laboratory and integrating it into scalable commercial hardware is where the quantum revolution actually reaches the consumer.
We are moving from the theoretical floodlight right to the silicon chip. Thank you for joining us in the classroom today, deep divers. Keep questioning the architecture of the problems in front of you, keep looking for those hidden patterns, and we will see you on the next one.